Good morning to all. Today's our topic is from Pradeep's Physical Chemistry book by Dr. S.C. Khetarpal. Our topic is polarization. If a cell consists of two reversible electrodes, then as the cell operates at each electrode, the rate of discharge of ions and the rate of their formation are equal. That is, electrode is in a state of equilibrium, hence there is no net flow of current. However, if the rate of discharge of ions is not equal to their rate of formation, equilibrium at the electrode is disturbed and a current may flow through the cell. This disturbance of equilibrium associated with the flow of current is called electrode polarization, and the disturbed electrode is said to be polarized. Such an electrode is said to behave as an irreversible electrode. The simplest type of polarization is known as concentration polarization, as briefly explained below. Suppose a reversible electrode is set up by dipping a metal rod in the solution of its own ions, then it will have a definite electrode potential called reversible potential depending upon the concentration of the ions as calculated by applying Nernst equation. If this electrode is made the cathode in an electrolytic cell and potential just greater than its reversible electrode potential is applied, then as reduction takes place at the cathode, the reaction Mn positive plus N electron to form M will start taking place, that is, discharge of metal ions will start on the metal electrode. As a result, the concentration of metal ions in the vicinity of this electrode will start decreasing. If the ions from the bulk of the solution do not diffuse towards the electrode to make up the loss, there is a fall in concentration of ions around the electrode, and hence its electrode potential will decrease in accordance with the Nernst equation. That is, E Mn N positive to M equals to E naught of Mn positive M plus RT upon NF ln of Mn positive. Similarly, if the electrode is made the anode in the electrolytic cell and a potential just greater than its reversible electrode potential is applied, then as oxidation takes place on the anode, the reaction occurring at the metal ions around the electrode will increase. If the excess ions do not diffuse away from the electrode into the bulk of the solution, the concentration of metal ions around the electrode will begin to increase, and so its electrode potential will also begin to increase in accordance with the Nernst equation. The increase or decrease in the concentration of metal ions around an electrode during electrolysis resulting into increase or decrease in the value of its electrode potential, then the reversible electrode potential value is called concentration polarization. Evidently, the concentration polarization arises on account of slow diffusion of ions from the electrode to the bulk of the solution or from the bulk of the solution towards electrode. This is supported by the fact that if the solution is stirred during electrolysis, concentration polarization is almost reduced to zero. This is because on stirring, quick migration of ions takes place. Decomposition voltage or potential. If two small smooth platinum sheets are immersed in a dilute solution of an acid or alkali and an increasing voltage is applied from an external battery so as to bring about electrolysis, placing a galvanometer in the circuit, it is observed that the current increases in a manner shown in figure. The significant current flows through the cell, that is, continuous electrolysis takes place with the evolution of H2 and O2 gas bubbles only when a definite voltage is applied. The point D corresponding to this voltage is found by extending the two lines so as to intersect at the point D. The voltage corresponding to point D is called decomposition voltage. Thus, the decomposition voltage of an electrolyte in a solution is the voltage applied to that solution at which steady electrolysis starts with the given electrode material. From the study of decomposition voltage of aqueous solution of a number of acid and bases, it is observed that with smooth platinum electrodes, the decomposition voltage is always nearly 1.7 volt. Hence, it was concluded that same electrolytic process occurred at the electrodes in each case. The only common process is possible at the electrode during electrolysis of all aqueous solution of acid and bases were the discharge of H positive ion at the cathode and OH negative ion at the anode to form H2 and O2 gas respectively. It is important to note that in an electrolytic solution, though the current is carried by all ions, but it is not necessary that the ions present in excess should be discharged on the electrodes. For example, in a solution of sodium hydroxide, though the current is almost completely carried towards cathode by Na positive ions, yet the ions discharged on the cathode are H positive ions when platinum electrodes are used. This is explained in terms of their discharge potential as described in the next section. Discharge or deposition potential. During the electrolysis of an electrolytic solution, if the electrode is reversible with respect to the ions in the solution and external voltage slightly greater than the reversible potential is applied, the discharge or deposition of the metal ions start taking place on the surface of the electrode. The potential thus required at which the discharge of ion starts taking place at a considerable rate is called discharge potential or deposition potential. The curve obtained is similar to that shown in the figure 6.18 and point D correspond to discharge potential. If a solution contains a number of different ions, each ion will be discharged when its discharge potential is reached. Since at the cathode reduction takes place, therefore the ions will be discharged in order of their decreasing reduction potentials or increasing oxidation potential. Greater the reduction potential, more readily it is discharged at the cathode. For example, an acidic solution of copper sulfate contains copper 2 positive ion and H positive ion. Their standard reduction potential are plus 0.34 volt and 0.0 volt respectively. Hence, copper 2 positive ion will be discharged first at the cathode. Similarly, at the anode, as oxidation takes place, the ions will be discharged in order of their decreasing oxidation potential. For example, in the electrolysis of acidified copper sulfate solution using anode of copper, the three anodic reactions possible and their oxidation potential as follows. Discharge of OH negative ions, their oxidation potential equals to minus 1.2 volt. Discharge of sulfate ion, SO4 2 negative ions, their oxidation potentials is equals to minus 2.0 volt. SO4 plus H2O to form H2SO4 plus half of O2. Now third one is oxidation of copper anode to copper 2 positive ion. Copper to form copper 2 positive plus 2 electrons. Oxidation potential equals to minus 0.34 volt. As oxidation potential of process 3 is maximum, therefore process 3 occurs in preference to first and second. Copper anode will dissolve. However, if the anode were made of platinum, then process first would occur, liberating oxygen gas. Over voltage or over potential. For the decomposition of an aqueous solution of an acid or alkali on electrolysis, the theoretical voltage required should be equal to the EMF of the reversible cell comprising of hydrogen and oxygen electrode. At ordinary temperature, this value is found to be about 1.23 volt irrespective of the nature of the electrolyte taken, which is acid or a base. However, the actual value of the decomposition potential at which the appreciable discharge of H positive and OH negative takes place and hence evolution of H2 and O2 gases takes place, that is appreciable current flows, is found to be much higher depending upon the nature of the electrode. For example, with platinum electrode the value is found to be 1.7 volt and with lead electrode it is found to be nearly 2.2 volt. This is evidently due to polarization effect taking place at the electrode. Using different metals as electrode, the potential at which the visible evolution of H2 and O2 gases occurred at the cathode and the anode respectively were found experimentally. The difference between the potential of electrode at which the evolution of gas is actually observed and the theoretical value for the same solution is called over voltage, originally called over potential. Having discussed concentration, polarization and over potential, it is important to understand that these are two different types of polarization. Concentration polarization arises on account of increase or decrease of the concentration of its ions in the vicinity of the electrode. On the other hand, overvoltage is a polarization potential which arises on account of some processes occurring at the surface of electrode which take place irreversibly and depend upon the nature of the electrode. Thus, the total polarization observed is the sum of both effects. To obtain the value of overvoltage, the concentration polarization is eliminated by the efficient steering of the electrolytic solution. The polarization voltage now observed, if any, is the overvoltage. It may be further pointed out here that overvoltage is also called bubble overvoltage because it refers to the stage at which the evolution of the bubbles of the gases commences at the electrodes. It is further important to note that overvoltage is determined at definite current density CD, which is the current per unit area of the electrode. At the applied voltage, current density can be made to have a definite value by connecting a variable resistance in the circuit I equals to E by R. Hydrogen overvoltage. The overvoltage observed when the evolution of H2 gas starts at the surface of cathode is called hydrogen overvoltage, or in general cathodic overvoltage. This is of greater significance because study of processes occurring at the cathode is more common and has greater importance in electroplating, etc. Factors on which hydrogen overvoltage depends. Current density. For a particular cathodic surface at a particular temperature, hydrogen overvoltage increases with increase in current density till ultimately it reaches a limiting value. Nature of metal used as cathode. For a definite current density, overvoltage depends mainly on the nature of the material of the cathode. Using cathode of platinized platinum at 0 current density, the hydrogen overvoltage is 0, as these are the conditions under which hydrogen electrode is reversible. However, hydrogen overvoltage using other metals as cathode has quite large values even at 0 electron density. This shows that these electrodes cannot function reversibly under any condition, which means that it is not possible to deposit H2 on them anywhere near their reversible potential. Hydrogen bubble overvoltage of a few cathodes of different metals at very low current density are given below. Platinized platinum, its overvoltage is 0.0, gold 0.02, iron 0.08, smooth platinum 0.09, silver 0.15, nickel 0.21, copper 0.23, cadmium 0.48, tin 0.53, lead 0.64, zinc 0.70, mercury 0.78. Temperature. Hydrogen overvoltage decreases with increase of temperature. Nature of the cathodic surface. For example, on smooth, shining and polished surfaces, the overvoltage is invariably greater than on a rough, pitted or etched surfaces. This is illustrated in the table for platinized platinum and smooth platinum surfaces. It may be noted that composition and pH of solution have very little effect on hydrogen overvoltage. Anodic overvoltage and oxygen overvoltage. It is observed that in the electrolysis of halides, the evolution of halogen at the anode takes place with a very small overvoltage, even at high current density. At low current density, the overvoltage becomes negligible. Thus, the deposition of halogen takes place almost reversibly. However, it is found that evolution of oxygen requires high overvoltage even at low current density. The value of oxygen overvoltage for a different anodic material at 25 degrees Celsius are given below. Platinized platinum 0.40, smooth platinum 0.72, gold 0.67, graphite 0.53, copper 0.42, silver 0.58, nickel 0.35. Applications of overvoltage. Number 1. Cathodic deposition of metal. Let us consider the electrolysis of a solution which is 1 molar in zinc sulfate and also 1 molar in sulfuric acid. We know that the reversible standard electrode potential E0 of hydrogen and zinc electrode are 0.0 and minus 0.76 volt respectively. Thus, discharge of H positive ions on the cathode should take place first, which will be reduced to H2 gas. When all the H positive ions have been discharged, only after that discharge of zinc 2 positive should take place, which will be reduced to zinc and deposited on the cathode. However, in actual practice, it is observed that liberation of H2 and deposit of zinc take place almost simultaneously. This is because with zinc cathode, hydrogen shows an overvoltage of 0.70 volt, which is very close to the reversible potential of zinc electrode. Thus, zinc can be deposited from acidic solution, which otherwise would not have been possible if there were no hydrogen overvoltage. In the other words, electroplating from acidic solution would not have been possible. Number 2. Separation of metals by electrolysis. If there were no polarization effect, that is, electrode was reversible, the metals start depositing on the cathode from the solution when the applied potential is slightly more than the reversible potential of that electrode. Hence, if a solution contained a number of metal ions, these could be deposited in order of their reversible potentials. For example, if a solution contains 1 mole per liter of each of a simple salt of silver, copper and cadmium, the deposition of metal will commence at 0.79, 0.32 and minus 0.40 volt respectively. That is, they will be deposited in the order silver, copper, cadmium. When a metal does not deposit reversibly, overvoltage has to be taken into consideration. By changing the temperature, the overvoltages are so adjusted that there is sufficient difference in the deposition potentials of the metals involved. For example, an electrolysis of ammoniacal solution of zinc and nickel at 20 degrees Celsius, both the metals are deposited simultaneously. However, at 90 degrees Celsius, nickel deposits first completely. Now the third one is dissolution and corrosion of metals. In general, a metal reacts with an acid to give H2 gas if its oxidation potential is greater than that of hydrogen, for which the standard value is plus minus 0.0 volt. Thus, lead, whose standard electrode potential is minus 0.13 volt or standard oxidation potential equals to plus 0.13 volt, should dissolve in HCl acid to give H2 gas. Similarly, zinc, whose standard electrode potential is minus 0.76 volt or standard oxidation potential equals to plus 0.76 volt, should dissolve in the acid even more readily to give H2 gas. But in actual practice, neither of the two dissolves in HCl acid to give out H2 gas. This is due to hydrogen overvoltage, which is 0.64 volt for lead and 0.70 volt for zinc. Now, if pure zinc is connected with a piece of copper and both are dipped into dilute acid so as to form a simple voltaic cell, the rate of dissolution of zinc increases significantly and hydrogen is liberated at the copper electrode. It has happened because zinc is less noble metal and hence dissolved to form zinc 2 positive ions at one electrode, that is anode, whereas H positive ion are discharged at copper cathode because overvoltage of copper is only about 0.2 volt. Same result will be observed if zinc containing copper as an impurity comes in contact with dilute acid. In general, if zinc contains an impurity of any more noble metal whose hydrogen overvoltage is low, zinc will dissolve and hydrogen will be liberated at the more noble metal. Thus, corrosion or dissolution of the zinc takes place. This can be further generalized by stating that if any base metal, that is less noble metal, for example, lead, iron, etc., contains impurities of nobler metals having low hydrogen overvoltage, the base metal will dissolve in the acid, that is corrosion of the base metal will take place and H2 will be evolved at the nobler metal present as impurity. This type of corrosion is therefore sometimes called as hydrogen evolution type of corrosion. It is important to remember that in the presence of air or oxygen or any other oxidizing agent which act as depolarizer, no evolution of H2 takes place because it gets oxidized as soon as it is formed. Hence, in such a case, the base metal will dissolve readily in the acid even if it contains impurities of metals having high hydrogen overvoltage. It is for the same reason that for pure zinc or lead which do not dissolve in acid dissolve readily if air or oxygen is passed through the solution. Thank you.